Hi all, myself Dr. K. Anitha, Associate Professor in the Department of EIE, VNR VJEC. I am here with electronic circuit title, that is oscillators. So we know that oscillators is a very important circuit in the electronics. Like amplifiers, we have number of applications in oscillators. So basically we have, first of all, we will see the definition of the oscillators. So the oscillator is an electronic circuit which produces periodic waveforms. These are oscillating electronic signals. Often we have sinusoidal waveforms or square waveforms or triangular waveforms. Number of different waveforms are produced by this circuit. Now basically oscillators convert direct current DC from a power supply to an AC alternating signal. Now these oscillator circuits are widely used in electronic devices. Common examples of these signals generated by oscillators include signals broadcast by radio and TV transmitters, clock signals, computers, and sound produced by electronic beepers and the video games. So other than that, we have number of oscillator applications. So coming to the classifications of oscillators, basically oscillator circuits are classified based on different criteria. First of all, based on the output waveform produced. So we may have sinusoidal waveforms or non-sinusoidal waveforms from the oscillators. So sinusoidal waveforms produce sine waveforms and non-sinusoidal waveforms. These non-sinusoidal waveforms produce square wave, triangular wave, rectangular wave, likewise different types of waveforms. Based on the circuit components, we have RC oscillators, crystal oscillators, and LC oscillators, inductive capacitive oscillators. Based on the range of operating frequency, we have low frequency or audio frequency oscillators, high frequency oscillators. So we can, each one of these oscillators have their own features and their own applications in the field of electronics. Oscillators are often characterized by the frequency of their output signal. Frequency of generation is very, very important in the oscillators. A low frequency oscillator is an electronic circuit that generates a frequency approximately below 20 Hertz. So over here we have 20 Hertz. From 20 Hertz we have the low frequency oscillators, and audio oscillators produce in the audio range about 16 Hertz to 20 kilohertz. An RF radio frequency oscillator produces in the range of about 100 kilohertz to 100 gigahertz. So and very important point with respect to the oscillators is it does not require any input signal. Of course, the DC signal is required for the active device to operate. However, as such, we do not give any input signal to the oscillator. It generates the oscillations. So we can have the oscillators which produce the output waveform of very high frequency, that is up to gigahertz. Now, it's not that simply we connect the circuit and we get the oscillations. Basically the oscillator circuit uses positive feedback. So we do have two types of feedbacks, positive feedback and negative feedback. In amplifiers, we use negative feedback. However, our oscillator circuit uses positive feedback. So in order to get the oscillations from the circuit of oscillators, we have to fulfill certain criteria, certain conditions. So these are called as Barkhausen criteria. These are the conditions for oscillations. What are these conditions? The total phase shift around the loop is 0 degrees or 360 degrees. In other words, we shouldn't have any phase shift, and the loop gain is unity. So these are the conditions. For example, you see this is the feedback used. Over here we have the positive feedback. A part of the output signal is taken from the amplifier circuit or from this circuit, and it is fed to the feedback network. So the output of this feedback network is connected back as input to the amplifier, and we observe here that there is no input signal. So this is an oscillator circuit which works without any input signal, which generates the oscillations. Coming to, we have seen the various types of oscillators. So under the classification of oscillators, see, based on the circuit components, we have LC oscillators. So I will discuss about the LC oscillators in this particular video. In this LC oscillators, we do have three types: Colpitt's oscillator, Hartley oscillator, and also Clapp's oscillator. So Colpitt's oscillator and Hartley oscillator are discussed in this particular video. So as we have seen, the amplifier circuit which has feedback, so we use positive feedback in the amplifiers. So in the feedback network, over here you see terminal 2 is the output terminal and 1 is the input terminal. So this output terminal, this is the feedback which constitutes the components. So it is depicted as, in general, this is the general block diagram of an LC oscillator. So it is depicted with Z1, Z2 and Z3. Over here, suppose if I talk about the Colpitt's oscillator, then I will have Z1 and Z2 as capacitors and Z3 as inductor. If I talk about the Hartley oscillator, then Z1, Z2 apparently becomes inductance, and these Z3 will become capacitor. So likewise, based on the type of the oscillator, you have to substitute, or you have to keep the place the component that is inductor or capacitor. So this particular amplifier, this particular block, it is nothing but active device, that is FET, BJT or op-amp. And as I already said, Z1, Z2, Z3 replaces the inductances or the capacitors. So active devices like FET, op-amp are used, and Z1, Z2 are the reactive elements, as I already said. Now the feedback circuit constitutes the tank circuit, which consists of the inductances and the capacitances. So it is called as, combination of this is called as tank circuit. So our LC oscillator works on tank circuit phenomena. Now the frequency, as I said, is very important with respect to the oscillators. Now the frequency, we have to determine the frequency of oscillations, or in other words, first we want to design an oscillator circuit for a particular frequency. So the frequency of oscillations for LC oscillator is given by 1 by 2 pi LC. So under root LC. So F is equal to 1 by 2 pi under root LC. So this is the frequency of oscillations for the LC oscillator. In this particular video, I will derive the equation for the Colpitt's oscillator, that is F equals 1 by 2 pi root LC. So this particular derivation is discussed over here. Coming to the circuit, here I have shown the Colpitt's oscillator. Over here you see BJT Q1 is the active device, R1, R2 are the biasing resistors, and it is used in common emitter configuration, and through the collector you have the output. So output is connected to the tank circuit. So this is the feedback circuit. This is nothing but the combination of capacitances and the inductance. In the general circuit, I have shown Z1, Z2. Over here, Z1 replaced by the C1, and Z2 is replaced by C2, and Z3 is L1. The output of the BJT is connected to this particular one end of the feedback network. The other one is connected to the base. Therefore, between the output and the input terminal, collector and base terminal respectively, for this active device, we have connected the feedback network. So over here we use the positive feedback. Now coming to the derivation of the frequency of Colpitt's oscillator, we will use the general expression for the frequency of oscillations. So the general expression for the LC oscillator is given by equation 1. HIE of Z1 plus Z2 plus Z3 plus 1 plus H of E Z1 Z2 plus Z1 Z3 equals 0. So this is the general equation. In the other video, I will discuss about the derivation of this general equation. So in Colpitts and oscillators, we can straight away take this general equation to proceed our derivation for frequency of oscillations. So I have taken the general equation. So this equation 1 is the general equation with the help of which we can proceed. In this equation 1, Z1, Z2, Z3 can be replaced with the components which we have used in the circuit. So coming to the circuit, we have used Z1 as C1 and Z2 as C2 and Z3 as L. So accordingly, we are substituting in place of Z1 1 by j omega C. And 1 by j omega C is the reactance of the capacitance we know. So hence we will substitute in place of Z1, Z2 and Z3 is j omega L. So in the general equation, we have Z1 plus Z2 plus Z3, this terminology. So I have substituted this and simplified so that coming forward, I can straight away substitute this for simplification. And I have also calculated Z1, Z2. So Z1, Z2 will come to 1 by j square omega square C1, C2. So these things I will straight away substitute in my general expressions. Now substituting these in my general expression, that is equation 1, which is again I have substituted over here. So we get this particular equation. Coming to after substitution, this particular equation consists of imaginary term and the real term. So we are segregating this imaginary part and the real part. That is, we will equate the imaginary part to get the frequency. For any oscillators, we have to equate the imaginary part to 0 to get the frequency of oscillations. Whereas we will equate the real part to 0 to get the conditions for sustained oscillations. Hence, in this particular equation, that is the previous equation, so we have the terminology with J, that is the imaginary. So this terminology with J, all the terms associated with J, so this is equated to the 0. This is the imaginary part. So HIE by omega of 1 by C1 plus 1 by C2 minus omega square L equals 0. So we have equated this to 0. Coming to simplification of this, try to obtain omega on the LHS. We know that omega is equal to 2 pi f. So substitution of omega, that is 2 pi f, gives me the frequency f in the LHS. So f is equal to 1 by 2 pi under root L into C equivalent. So this is the frequency of oscillations for Colpitts oscillator. So Colpitts oscillator, the C equivalent is given by C1, C2 by C1 plus C2. So we have to substitute the C1, given the values of C1 and C2, we will substitute and determine the value of C equivalent, which will be apparently substituted in this frequency of oscillations, that is C equivalent. And then with the help of this, we will get the equation for the frequency, that is the value of frequency of oscillations in the Colpitts oscillator. Similarly, if we are working with the Hartley oscillators, then Z1, Z2 will be substituted with the L. That is, Z1 will become L1 and Z2 will become L2 and Z3 is C. And substitution of the reactance values and the frequency will become L equivalent. However, we will see that. And the other part is make the real part to 0. Equating the real part to 0 and simplifying, we will get the HFE, which is the condition for sustained oscillations. In oscillators, not only generating the oscillations is important, getting the sustained oscillations is very important, because oscillations, we may have damped oscillators, for example. So we have, this is the oscillation, that is sustained oscillation. So we may have sometimes, if the designing is not proper, the oscillations will be dying off. So this is called as damped oscillations. So damped oscillators are not preferred. So we have to we have to maintain the condition for sustained oscillation. Sometimes we also may have oscillations like this. So these two are not preferred. However, we should have sustained oscillations. So for Colpitz's oscillator, we have derived the frequency of oscillations f equals 1 by 2 pi root L C equivalent. Thank you so much.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.